Now you should know what relations are, what equivalence relations are. We are now looking at equivalence classes. All right. So if I start now with an equivalence relation, we've seen some examples of equivalence relations. If I start with an equivalence relation, then an equivalence class of one of the elements of the set. So each element of the set has an equivalence class. We'll see sometimes they're the same. We'll see what they have in common and so on. But each element of a set has an equivalence class. Now, what is that equivalence class? Those are all the elements of that set that matches with it, with the relation R. So if I've got a set A, the relation is R, then the equivalence class, and we showed with a bar, is all the x's in that set, so that ARX is true. So let's build some equivalence classes and see what they're going to look like. So here I've got P. I know it's an equivalence relation. I've tested it on all three. It's reflexive, it's symmetric, and it's transitive. So now I want to see what will the equivalence class look like. So in general, the equivalence class of some element A is going to be the set of all B's or X's, whatever you want to call them, given APB is true. So what does that look like? That's all the B's given 3 is a divisor of A minus B. All right, these symbols look the same, so let me rather use colons. What does that mean? That's all the B's given A minus B is equal to 3 times K, where K is some integer. All right, so that's what it looks like in general. It's a set of all B's that match with that A. So let's look at specifics. So let's look at the number 2. 2 is an integer, so I can do this for any integer. 2 is an integer, so the equivalence class is all other integers, because P is defined on Z. So I'm looking at all the integers such that, so it's all the B's given 2 minus B is equal to 3 times K, where K is an integer. That's what it looks like. It's all the B's for which 2 minus B is equal to 3 times K. Now that's a bit clumsy if I'm trying to generate those B's, so let's write it better. It's a set of all B's, make B the subject of the formula. B is equal to 2 minus 3K. And K is some integer. Right, well, there's going to be an infinite number of elements of this set. Because remember, we're looking for all the numbers for which 2 minus that number is divisible by 3. So all the numbers for which 2 minus that number is divisible by 3. So we're going to generate an infinite number of integers. I can't write them down. So I'm going to just get into small grouping. So I'm going to show how this set looks. So let's start in the middle. If K is 0. If K is 0, B is going to be 2 minus 0, so that is 2. I'm writing it in the middle. I'll show you why. If K is 1, what happens? 2 minus 3 times 1 is 2 minus 3, so that's minus 1. So that's on this side, because I'm getting smaller. If K is 2, I've got 2 minus 6. 2 minus 3 times 6 is 2 minus 6, and that's minus 4. So we can see the pattern being established. It gets less by 3, and so on and so on. In the other direction, if K is minus 1, I've got 2 plus 3, that's 5. So it gets more by 3. Then it gets more by 3, and so it carries on. And that is what the equivalence class of 2 looks like. Now, let's just take a look here. Does it work? Well, what must happen? This must be true for each and every one of those linked to 2. So 2 minus 2 must be divisible by 3. It is. 2 minus 5. 2 minus 5 is minus 3. That's divisible by 3. What about 2 minus minus 4? 2 minus minus 4 is 6. 6 is divisible by 3. So this whole equivalence class of 2 gets generated. Minus 4, minus 1, 2, 5, 8. We keep getting bigger and smaller, but it's, as you can see the pattern, it's 3 added every single time. All right. So let's look at another number. Let's look at 5. We've got the same equivalence class. We look at 5. Same equivalence relation. So if I look at 5, the equivalence class of 5 is all the B's or X's, whatever letter you want to use, such that 5 minus X is equal to 3K, where K is an integer. All right, so what will that look like? That's all the X's given X is equal to what? 5 minus 3K. where k is an integer. So let's generate that set. That's going to be, if k is 0, I've got 5. If k is 1, I've got 5 minus 3 is 2. If k is 2, I've got 5 minus 6 is minus 1. It keeps getting less by 3. If k is minus 1, I've got 5 plus 3, which is 8, so it gets more by 3. The next one will be 11, and so on. So 5 minus any of these numbers is divisible by 3. But now let's just rewind a little bit. We looked at the equivalence class of 2. It's minus 1, 2, 5, 8, minus 1, 2. They're the same. Are they exactly the same, or do they share some elements? Well, the equivalence class of 2, if we look at those elements, 2 is in there, 5 is in there, and I keep adding 3, and I keep taking 3 away. In the equivalence class of 5, 2 is in there, 5 is in there, we keep adding 3, we keep taking away 3. They are exactly the same. So that's interesting. We'll look at that concept a little bit later. All right, now are all the equivalence classes going to be the same? Let's look at 1. Because that'll be boring if they're all the same. 1 is all the x's. Given 1 minus x is equal to 3k, where k is an integer. Okay, so if I look at that, that's all the x's given x is equal to 1 minus 3k, where k is an integer. So I start where k is 0, then the number 1 is in there. All right, it's not the same as the previous two. If k is 1, I've got 1 minus 3, which is minus 2. If k is 2, I've got 1 minus 6, which is minus 5. So I keep jumping by 3 again, but from a different starting point. If k is minus 1, I've got 4. If k is minus 2, I have 1 plus 6 is 7. All right, so it keeps getting less by 3 and more by 3, but it's not the same as the previous one. All right, what about the equivalence classes of 0? So all the x's given 0 minus x is equal to 3k, where k is an integer. So that's just all the x's equal to 3 times minus k. Or minus 3 times k, where k is an integer. So what will those look like? Well, I can start in the middle. If k is 0, I'm going to have 0. If k is 1, I'm going to have minus 3, minus 6. If k is 1, I'm going to have 3. Minus 1. If k is minus 2, I'm going to have 6, 9, and so on. So it keeps getting bigger and smaller. It changes by 3. Now the 3 is significant because our original equivalence class looked at divisibility by 3. But now we've seen the equivalence class of 2, of 1, of 0. They're all the same. So it keeps jumping. Now, please notice, 1 is in its own equivalence class. 0 is in its own equivalence class. 2 was in its own equivalence class. 5 is in its own equivalence class. So the question is, how many different equivalence classes are there? We can look at the equivalence class. What about negative numbers? Minus 1, we look at all of the integers. So minus 1 is all the x's, given x is equal to, well, let's first write it. Minus 1 minus x is equal to 3k, where k is an integer. So that is all the x's, where x is equal to minus 1 minus 3k. Where k is an integer. It's always important to say where k come from. What will those look like? Well, if k is 0, I've got minus 1. If k is 1, I've got minus 1 minus 3, which is minus 4, minus 7. If k is minus 1, I've got minus 1 plus 3 is 2. Are we getting back to 2, 5, 8? So we're circling around again. All right. This is the same as the equivalence class of 2, which was the same as the equivalence class of 5. Now, so we can generate all these equivalence classes. So what you need to find out is how many are there going to be until I start repeating. So you can play with these equivalence classes. What you're going to see is there's actually just 3 distinct ones. 0, 1, and 2. Any equivalence class was going to be equal to one of those, but we'll look at this concept again at a later stage.